In this chapter, we're going to take a look at differentiation in more depth. Now, before we do that, we're going to first do a small investigation. If I'd given you the function as shown on the screen, and I'd asked you to find the derivative of this function, at this stage of your career, you only know about the power rule. Now, the power rule says that you can only do differentiation if you have terms and if you have your x's only in the numerator. Well, clearly there's a problem over here because I have a bracket squared. In other words, if I wanted to use my power rule, I would first have to multiply out my two brackets, getting 4x squared plus 4x and plus 1. And now I'm able to differentiate. Finding the derivative of this function, my derivative, remember, in the important variable x, is going to be as follows. Do you remember how we did this? We said take a look at the exponent of the variable. In the first term, the exponent is 2. That exponent becomes a coefficient factor for that same term. As there was already a coefficient of 4, I now have 4 times 2, which gives me 8. And then I minus 1 from the original exponent, and 2 minus 1 is 1. Repeating this procedure all the way through, I find that I get 8x plus 4 as the derivative. Let's see what would have happened if I had tried to find a derivative of my composite function. Now, can you see that there are in fact two functions in this function given over here, the function of y? The inside function is 2x plus 1. The outside function is x squared. In other words, if I had written this function y as f of g of x, I would have known that the f of x function was in fact going to be x squared, and the inside function g of x would have been the function of 2x plus 1. Now what I'm going to do is I'm going to find the derivative of the outer function and then times that by the derivative of the inner function. In other words, if I use this method, I'm going to say dy by dx is going to be found by finding the derivative of the outer function. Now, when I want to find the derivative of the outer function, I treat this as x. In other words, I want the derivative of x squared. So I'm going to get 2 times by whatever I had for g of x. Now I need to times that by the derivative of the inner function, and that is going to be 2. Let's work out what this is if I simplify it. Can you see that if I say 2 times 2 times 2x, I'm going to get 8x, and then timesing 1 by 2 by 2, I get plus 4. In other words, I've got exactly the same answer. Let's try this again in another example. First of all, just using the power rule, I cannot use the power rule until I've expanded my function that I've got over here represented by y. So in this example, when I expand, y is in fact going to be 4x to the 6 minus 12x to the 4 plus 9x squared. Now finding the derivative of this function, my derivative in the variable x is going to be 24 x to the 5 minus 48 x cubed plus 18x. Now I'm going to try and find the derivative again, but this time I'm going to look at my composite function. In this function y, it is made up of two parts. My outer function, the f of x function, is in fact going to be x squared. My inner function, g of x, is the function of 2x cubed minus 3x. Now if I want to find the derivative, then I need to find the derivative first of the outer function. The derivative of the outer function, dy by dx, is going to be 2. Remember, g of x is still there. I haven't found the derivative of that yet. Now if I find the derivative of the inner function, I need to find the derivative of 2x cubed minus 3x, and that's going to be 6x squared minus 3. At this stage, you can't really see that this is the same as my answer when I first expanded and used the power rule. But if I multiply out these brackets, I do find that my derivative is exactly the same. So in other words, the derivative of this function, whether I multiplied out and I used my power rule, or I found the derivative of the composite function, would have given me the same answer of 24x to the 5 minus 48x cubed plus 18x. It seems that we're starting to develop a pattern over here. I want to do one more example with you just to make sure that it works. In my previous examples, all of my variables were in the numerator. So I want to try one now with my x in the denominator. First, trying to do this using the power rule, I must expand. And when I expand this function of y, remember I have to write the bracket times by itself. In other words, I'm writing 2 plus 1 all over x, all times by 2 plus 1 all over x. The power rule cannot be used unless I have just terms and all my variables in the numerator. First multiplying out, I find that this is going to give me 4, and then I've got 2 all over x, and then 2 all over x, and then 1 all over x squared. You can see that the middle two terms could have been added. So now I have 4. If I add them, I've got 4 all over x. But I can't use the power rule while that x is in the denominator. So at this stage, I'm going to take it up. And then lastly, that last term is going to be x to the minus 2. Now I'm able to use the power rule to find the derivative of this function. And the answer is going to be minus 4 x to the minus 2 minus 2 x to the minus 3. If I write this derivative using positive exponents, I could have written it very neatly as follows. Now what I want to do is I want to take a look and see if I found the derivative of the outer function and I times it by the derivative of the inner function, would I get the same result? First of all, finding the derivative of the outer function, I want to find the derivative of 2 plus 1 all over x all squared. If I find that derivative, I'm going to get 2 and then 2 plus 1 all over x to the 1. Now I want to find the derivative of the inner function. Now the inner function is 2 plus 1 all over x. If I want to find the derivative of that using my power rule, my x must be in the numerator. So that you can see what I'm doing, I can write my original function as follows. You can see now for the inner function, when I find the derivative of 2 is 0, and the derivative of x to the minus 1 is going to be minus, and then x to the minus 2. Now let's see if we multiply out, are we going to get the result that we had above? When I multiply out over here, it's much easier multiplying out if all of my exponents are positive. So first of all, I'm going to multiply the 2 into the first bracket, which is going to give me 4 plus 2 all over x. And then the second bracket actually could be written as minus 1 all over x squared. So lastly, multiplying this last factor into the bracket, I find that the derivative could have been written as minus 4 all over x squared, and then minus 2 all over x cubed. We have very successfully now investigated a new way that we can find the derivative of a function if I have a composite function. And this rule is called the chain rule. When I want to find the derivative of a composite function, then I find the derivative of the outer function, and I times it by the derivative of the inner function.